Hi, my name is Zhening. In this video, we present OpenIns3d, a new 2D input-free and powerful pipeline for 3D open-world scene understanding at instance level. Background: computer vision is going through a transition from the previous closed-set perception to open-world perceptions. In the closed-set setting, the model can only handle predefined classes during the training process. On the other hand, the open-world perception aims to understand unseen, diverse, and freely described objects. In these directions, 2D open-world understanding has made substantial progress, not only capable of understanding new concepts and conducting high-accurate segmentation or detection tasks, but can also handle extremely complex text input, which might require reasoning and word knowledge to process. In contrast, 3D open-world understanding is still in its early stage. The lack of progress is partially due to the absence of large-scale 3D text dataset. As a result, common approach for 3D open-world understanding rely on using images to bridge the gap between 3D and languages. Related work. There are some notable work in these directions. We categorize them into three groups. The first one is feature distillation group, such as OpenScene and Clip-to-Scene. Both of these methods rely on the precise matching between pixels in images and points in 3D. The language-aligned features in pixels are distilled to 3D backbones. The second group focuses on building 3D text pairs. Typical work are the PLA families, including PLA, Regional PLC, and Lois 3D. In this direction, they construct 3D text pairs at different scales with the help of image captioning model. The third group is clip and projection group, including OpenIns3d, which is a coherent work of ours, and OE3DT. They first crop out objects or instance from RGBD images and use clip models for understandings. The results are then projected back to 3D space. While some of these methods achieve the reasonable result, one common issue is that in their prerequisite, both reconstructed 3D point cloud and well-aligned 2D images are needed. This poses a challenge for scenarios where 2D images are not available. Differently, in our work, OpenIns3d only requires 3D point cloud as input to perform 3D scene understanding tasks at instance level. Motivations. Why is 2D input-free framework interesting and useful? We present two reasons. First of all, in many circumstances, 2D images or the information required to align 2D and 3D might be missing. This often happened with LiDAR point cloud, where 2D images might be missing, photogrammetry point cloud, where the depth information might be missing. This also applies to point cloud generated from the registration of multiple scans or converted from 3D simulators, CAD models, etc. In real applications, the alignment information might be missing in the transferring process, and the 2D images might be removed to save storage. An example is in ScanNet V2, the 3D point cloud for a scene is typically 3 MB, while the image package for a scene is typically 3 GB. The second reason is that, we argue, if well-aligned 2D data is available, it is much easier to approach 3D open-world understanding from a 2D understanding plus 3D projection approach. Since 2D open-world perception are more advanced and the complete projection matrix and depth information are available, we can firstly conducting open-world understanding in images and then projecting the result directly to 3D using the projection matrix and depth information. A proof of concept has been done in the work SAM3D, which uses SAM to learn instant mask in posed images and projecting the result to 3D space. In conclusion, we believe a 3D open-world model should ideally work without the need for corresponding 2D images. This is the overall pipeline of OpenIns3d. With the 3D input point cloud, first, we use the mask proposal module to learn class-agnostic mask proposals. Then, we use the snap module to generate synthetic scene-level images and construct class lookup tables. Eventually, we search the class lookup table to assign category names to each mask proposal. Let's dive into the details of each module. Given a 3D point cloud, the mask proposal module is used to learn 3D mask proposals, which is adapted from Mask-3d with all the components requiring classification labels removed. We introduce a scoring module to produce scores for each mask proposal. The generated proposal undergo mask score thresholding and mask filtering, resulting in a filtered high-quality mask proposal. After exploring various rendering approaches, we propose the following scene-level image rendering technique. Firstly, point clouds of the scene are projected. We position the camera at the top of the scene evenly to capture the scene from different angles. The intrinsic matrix is calibrated to place the scene at the maximum proportion of the images. Then, mask proposals are projected using the same camera models to form mask pixel maps, which later will be used as guidance in the lookup module. The projected images are then fed into a 2D open world detector to extract all interesting objects and their pixel locations. The detection results are stored in the class lookup tables as a final output of the snap module. We search through the class lookup table to assign category labels to mask proposal. The mask to pixel map, which stores the mask locations, is used as guidance. The best match is determined by calculating the IOU values between the projected mask proposals and the detection results. We ensemble the result from the multi-views to form more confident detections. We conduct a similar approach at local level to encourage detection. The result from both global and local detection form the final output. This mask, snap, and lookup module not only requires no 2D input, but also offers several advantages compared to other methods. First of all, since we outsource the open world detection task to 2D models, the open world models can be switched easily without retraining, giving OpenIns3d a compelling advantage of evolving seamlessly with the fast-developed 2D models. Second, compared to object or instant type of rendering, the scene-level rendering approach requires less rendering effort. Lastly, the impressive complex input handling capability of some open-world models can be transferred directly to 3D with the OpenIns3d framework. As a result, OpenIns3d can also conduct 3D reasoning segmentation tasks that is unseen in other 3D framework before. Although OpenIns3d requires no 2D image input, it still achieves impressive performance on both open vocabulary instant segmentation and detection benchmarks, outperforming other methods by a large margin in both indoor and outdoor datasets. Specifically, we compare our method with PLA families, following their base and novel class split. PLA is trained with base category and tests on the novel categories. Moreover, we test our results on outdoor dataset STPLS3D compared with PointClip and PointClip v2. In object detection task, we convert the mask proposals into bounding box and achieve significant improvement compared to all other models. Here are some demonstrations of 3D reasoning segmentations achieved by OpenIns3d. We showcase zero-shot instant segmentation result on ScanNet v2. S3DIS, and outdoor STPLS3D. We will release our code very soon on Points at GitHub group. Thank you very much.